Okay, today I want to go through chapter 17. Thanks for attending this. We're going to narrow down the learning objectives here. So let me write this as a new slide here. All right, so as far as the learning objectives go, we are going to first do the definitions of what an acid and a base are. So there are just three definitions. There's Arrhenius and Bronsted-Lowry. And Lewis. All right, then we're going to look at Bronsted acid-base reactions after that. So, actually, we've already done this, Bronsted acid-base reactions, when we were talking about chemical reactions. So this is just a review of that. And then third thing, we're going to look at water autohydrolysis. Okay. Water hydrolysis, KW, and pH. And so this is going to be for water, this is going to be for acid solutions and base solutions. So those are the three things we're going to focus on. And so rather than doing a whole bunch of slides, let's just look at the definitions here on one slide. It should be enough. And so when we're looking at the definitions, Arrhenius is very simple. Arrhenius is an acid is just defined as H plus in solution, or H3O plus, aqueous. And so anything that gives H plus or H3O plus in solution in the base is OH minus, aqueous. That's Arrhenius. So we aren't going to spend much time with Arrhenius. Bronsted, yes, we're going to spend more time thinking about acids in terms of Bronsted-Lowry, in which an acid is a proton donor and a base is a proton acceptor. And so we have different so an example of the reactions we'll look at here, but we'll go on to Lewis next. Let's see, does this work? Okay, now. So for Lewis, an acid is defined differently. An acid is an electron pair acceptor. And a base is a electron pair donor. So when we look at the acid-base universe, let's try to illustrate this over here. So acid-base universe. That is, if we look at all the acids and bases in the universe, they all are Lewis acids and bases. However, they aren't all Bronsted, and so Bronsted is a subset of these. And so it's a smaller part of the acid-base universe. This would be the Bronsted. And so all Bronsted acids are Lewis acids, but not all Lewis acids are Bronsted acids. Just oh no. All right, and then Arrhenius is even a smaller subset of this, and so what we can do is we don't even need Bronsted. We could just label everything as a Lewis acid in the base. But we don't do that because Bronsted follows a simple pattern. And since Bronsted follows a simple pattern, we retain this definition. And so if something acts as a Bronsted acid, sometimes it's just easier to analyze in terms of a proton being transferred from the acid to the base rather than electron pair, although sometimes both are equally as easy to visualize. But anyway, let me give you an example of some reactions here. Actually, I'm just going to insert a slide here. Arrhenius are pretty straightforward. There's only one thing, and that is H plus OH minus yields H2O liquid. That's it. Bronsted, let's look at some examples here. This would be the one and only example for Arrhenius. For Bronsted, there's lots of examples. And so we could have things that look like a metathesis and are metathesis reactions. This would give us sodium chloride and water, salt and water. Or we could have things that are less like metathesis. So for example, we could have HCl gas, hydrogen chloride gas plus ammonia gas. And this forms ammonium chloride solid. So it need not be aqueous like Arrhenius. That would be a Bronsted example. Lewis, all of the above are Lewis. So here, what we typically think of in terms of Bronsted is a proton being transferred from the acid to the base. And so we say proton transfer reaction here. But this reaction can be also visualized as a Lewis acid-base reaction. And so in this case, the base, ammonia, attacks the acid. And this is in the gas phase, so even though HCl is a strong electrolyte, in the gas phase it's going to just form hydrogen chloride molecules. And what we have here is, rather than the proton being transferred, we have the electron pair attack here. And so that's going to hit this hydrogen and essentially knock it off and leave these electrons here. And so what we end up with is essentially proton being transferred, but you can see the base, the lone pair here, the base attacks the acid, plucking that hydrogen off the HCl molecule. And so we'll be left with ammonium. This is going to have a positive formal charge here, and chloride. We'll have a negative formal charge, and then we could put the net charges around the bracket like this. And this would just form an ionic lattice here. This would be an example of a Lewis. All of the above here are Lewis. But we have ones that are a bit more involved. So for example, CO2. And this is Lewis acid. And CO2 has no protons to donate, so it wouldn't qualify as a Bronsted. but it does qualify as Lewis acid. So if we take CO2 and react it with a base like water, water can go either way. It can act as an acid or a base. And the same thing with CO2. CO2 has these lone pairs on the oxygen that can also react as a Lewis base. But a Lewis base is going to have a lone pair, and it should have like a delta minus. It should be electron rich and electron poor. But basically what we see here is there's going to be this delta minus. Oops. Let's try to make that narrower. We got this delta minus here in the lone pair. So delta minus lone pair. And then over here, this is going to be delta plus. We got the delta pluses over here on the hydrogens. We're going to have the delta plus on the oxygens here. And so we'll have this come in and attack. So the base attacks the acid. In this case, the acid is this site here, the carbon, this specific atom. And we can't have too many electrons. We have to obey the octet rule, and so we can't exceed it. That means one of the bonding pair, the double bond here, is going to have to break and maybe go to that oxygen, either one of these oxygens here. And so what we end up with is a structure that looks like this. Something like this. Now, looking at the formal charges here, the formal charge on this oxygen is now negative. It's 2, 4, 6, 7 electrons. And the formal charge on this oxygen is positive. Well, this structure here with this positive oxygen here is like hydronium, H3O plus has a structure like this. And what happens is this positive formal charge on this oxygen makes these hydrogens much more acidic, because this oxygen is going to be much more electronegative, and it's going to suck more of the electron cloud density towards it, and so this is acidic. And this oxygen here is like hydroxide. And so we have like an acid and a base in the same molecule. This whole thing's neutral. Everything obeys the octet rule, but the formal charge is a bit high, so this isn't as stable as what we just came from. And so what can happen is this can go backwards and reform what we have. Or what we can have happen is this. We can have this twist around so that this oxygen comes over here and abstracts this. So what happens is there's free rotation around this, and so this could rotate over and go in proximity of this oxygen here. And if that's the case, then this oxygen will pluck off that hydrogen, leaving this pair of electrons behind here. And so this would rotate around, which I'm not going to draw. And when that happens, this oxygen here picks up the hydrogen over here. Let's do that one more time. It plucks the hydrogen off over here, and we end up with something like this. And this will lose that hydrogen, but will gain that lone pair, that bonding pair that was there. And then we have this. So this can also go backwards too. It's reversible. This ends up forming carbonic acid. And so what we have is the reaction overall is CO2 plus H2O liquid can yield H2CO3 aqueous carbonic acid. And so what happens is if there's CO2 that's bubbled in water, it increases the acidity of the water by making this carbonic acid. That's one way of thinking about it. All right, so those are examples of reactions here. All right, so let's take a look at some of these slides here. And so this Arrhenius, H plus aqueous, Arrhenius acid, Arrhenius base, hydroxide. Acids, this is what we call an indicator. If you use red cabbage juice, the color depends on the pH, and pH describes some of the acidity. And so more acidic means a lower pH. More basic means a higher pH. And then we have neutral. Neutral pH, or neutral acidity and basicity, is pH 7. That would be neutral. And so this would be lower pHs, that is less than 7, and this would be higher pHs, greater than 7. And the color changes depending on what the pH is. Now, this might not be exactly in the 7s, you know, more basic. Actually, more basic just means that it has a higher pH. Basic is greater than pH 7, but more basic could be like going from pH 2 to pH 3. pH 3 is more basic than pH 2. However, pH 3 is still considered an acidic solution. And so higher pH, or we should say greater than 7, is what we call basic solution. And just more basic doesn't necessarily mean it's basic. It just means it's more basic. And then a pH less than 7 just means it's acidic. Acidic here. But you know, I don't know where red cabbage, where the pHs lie, and so we'd have to see. But basically, the pH increases as we go across. Now, does it become yellow? Well, yeah. Where the cutoffs aren't necessarily. That is, this isn't necessarily pH 7 here with the green, is what I'm saying. Over here, this is calcium carbonate. Calcium carbonate is attacked by acids, you know, H+. Here, this is solid, and we need 2 of those. And what this forms is calcium 2+ plus H2O liquid plus CO2 gas. So any acid will do here, in this case, giving H+ to this Bronsted acid. But even Lewis acids, when dissolved in water, can form H+ like CO2 did. This is the metathesis, or a just a Bronsted. So, acid-base reaction. Over here, this is a redox reaction, and this is zinc with hydrochloric acid. So solid zinc metal plus 2 HCl. This is a single replacement reaction. It's going to form zinc chloride plus hydrogen gas. This is because acids are also oxidizers, and so this is acid-base. This is a redox reaction over here, because acids are also oxidizers. And that is 2H plus 2 electrons yields H2 gas. And so it's not, zinc is not a base. This is not an acid-base reaction. Zinc is a reducer, HCl is an oxidizer. And so HCl can also be a precipitating agent, you know, for chlorides, which we used in qualitative analysis. We used HCl not as an acid. We used HCl as a precipitating agent in metathesis reaction. And so that's that. Now, the lights went out, but the lights. All right, when we do Bronsted acid-base reactions, you know, we're setting up a competition. And so here, if we look at this reaction, we have ammonia, which is going to be the base. And ammonia is going to attack the acid and pluck the proton off, in this case. And so this is a Bronsted acid-base transfer of a proton. Now, when we look at the driving force, we have to look at the reverse reaction. And so if we were to reverse this reaction, then going backwards, ammonium, which was formed as a product here, come on. Let's see, is this working? Yeah. this would be the acid going backwards, and this would be the base. So ammonium donates a proton to hydroxide, forming ammonia and water. All right, now, this is what we call a conjugate pair. So the base, ammonia, and the acid, ammonium, are a conjugate pair. And we see that in the table. So for example, our table is a table of acids. In our table of acids, we'll have ammonium, this is an acid, and its conjugate base, which would be ammonia here. This would be a base. And we have a conjugate relationship. The conjugate relationship is the stronger the acid, the weaker its base. The stronger the base, the weaker the acid. And so it has to be that way because a strong acid doesn't really want a proton, whereas a strong base does. And so there has to be a seesaw relationship there. Okay, now the other conjugate pair is water and hydroxide. You know, water is the acid on this side, and hydroxide is the base on this side. And so water would form the other conjugate pair here. And so this is what we see in the acid-base chart. And so this is why we see the inverted relationship. That is, as the acid strength increases this way, the base strength decreases this way. So it's like this seesaw relationship. So the acid is very strong, then its base, conjugate base, is going to be weak. If the base is very strong, its conjugate acid is going to be weak here. And so we have this kind of relationship. And so this is a conjugate pair here. This would be a conjugate pair here. I'll show you on the chart when we get to it. So what we do when we look for driving force is, are we going from strong, strong to weak, weak, or weak, weak to strong, strong? You know, that's what we look at. In this case, this is, when we're comparing the two bases, we compare ammonia versus hydroxide. Well, we know hydroxide is a strong base, so this is strong, this is weak. So this is not favorable. And then water versus ammonium, water is weaker, this is stronger. So the driving force for this reaction is actually reverse here. They're showing go both ways. It can go both ways depending on how steep the climb is. As we had talked about earlier, you know, not everybody in the population has the same energy. You know, there's a Maxwell-Boltzmann distribution of energies. So it's like a group of bicyclists. Some, maybe a small fraction of the bicyclists can make it to the top of the hill. And that's what we have here. And we've seen this reaction before in electrolytes. You know, weak bases are weak electrolytes. And bases hydrolyze water weakly. And so a little bit of this reaction happens. But however, it's favored downhill. Very few of them can make it uphill here. So if we have everybody uphill here, they're all going to fall down. So if we start off with ammonium and hydroxide, that's unstable, that's going to fall downhill. Whereas if we start off with ammonia and water, that's pretty stable. And just a very small fraction will make it up the hill here. And so I'll show uneven arrows here, but this is a dynamic equilibrium. And so you could show the arrows equal here. You know, some of them will make it up here, and then we'll get a constant. Let's say 5 of 100 bicyclists can make it up here. So if 5 make it up here out of 100, then, you know, eventually those fall back down, but another 5 will replace those. And so there's a constant. So whatever rate we have coming down, 5 coming down, was going to be replaced by 5 going up. And so drawing equal size arrows is fine like this, but I draw uneven size arrows like this, not to show the rate, but to show which side's uphill and which side's downhill, or which side's favored, basically. Not that the rate forward is a lot slower than the rate reverse, that kind of thing. This is just kind of generic. Amphoteric, this is something you need to know. Substances that can behave both as an acid or a base, you know. And the way amphoterics behave depends on how it reacts, depends on what you react it with. How it reacts depends on what you react it with. Other species, you know, what species you're reacting with. That's what I mean by that. And then, well, of course, we have forward and reverse reactions because we got to look at this as like a competition, which side's favored. Here's another example of a Lewis acid-base reaction. In the Lewis acid-base reaction, the base here, the lone pair, attacks the acid. This is a good acid here because this doesn't have an octet. Fluorine does not double bond. Even though fluorine has electron pairs here, it could form a double bond. However, that would screw up all the formal charges. It would give fluorine a positive formal charge and boron a negative formal charge, which is not going to happen. So another way that boron can get an octet is by being attacked by a Lewis base like ammonia. And this is what we call Lewis acid base adduct. So the fluorine holds on to all its electrons here. And so I'm going to just pencil those in here. And so another example. And there's no proton donor, proton acceptor here. And so another example of that. So here's a summary slide of the definitions. And we talked about the conjugate acid-base pairs. You have to just see, when HA, the acid loses a proton, it forms its conjugate base A minus. When B gains a proton, it forms HB plus. And so these would be, HB plus would be a conjugate pair, and HA and A minus would be a conjugate pair. Here we have acetic acid, CH3COOH, and water. So this is the acid. Water is amphoteric, it could go either way, but acetic acid is a much better acid than water is, and therefore water will act as the base. And so water will pluck the proton off acetic acid, form hydronium. And so water and hydronium are a conjugate pair, and then acetic acid and acetate are a conjugate pair. So that would be the conjugate pairs. Then when we do the driving force, we just do it as normal. This is an acid, this is the acid, and which is stronger? Well, hydronium is a stronger acid. So again, this is going from a stronger acid, actually not, it's going from a weaker acid to a stronger acid. And the base is the same. It turns out water is a weaker base. It has to be. It has to go weak, weak, or strong, strong. They have to be the same on both sides to a stronger base. So this is not favored in the forward direction. And so what we say is acetic acid is a weak acid. Weak acids only partially hydrolyze water. And so this is something where, some of the population will be able to make it up the hill to form hydronium and acetate, CH3COO minus, whereas acetic acid is much more stable, and water. But, some of these will have enough energy to make it to the top. And we'll have a dynamic equilibrium set up that way. The dynamic equilibrium is just showing this here. There'll be a stable amount. So let's say 5% or whatever, 1% of the population can make it up. Then it's going to be a stable 1% because they might not stay there forever, but if they drop down, another will take its place. And so there are two ways to show this dynamic equilibrium. One with these uneven arrows showing the kind of the uphill direction, downhill direction for this, or which side's favored, the reactant side's favored, or equal-sized arrows showing that, whatever we have going up is the same going down once we've hit the state of dynamic equilibrium. These are conjugates. This is amphoteric, a bicarbonate. What is the conjugate acid of ammonium? Ammonia, okay, if we're looking for the conjugate acid, this must be the base. And so the base plus the proton will give us ammonium. That would be the conjugate acid. What is the conjugate acid and the conjugate base of this? Okay, the conjugate acid is we're going to add a proton. This is the base. We add a proton, we get H2CO3. That would be the conjugate acid. And the conjugate base of this would be, okay, this is the acid now. If this is the acid, then the conjugate base would be carbonate. And so this would be the conjugate acid, this would be the conjugate base, and then bicarbonate can go either way. We have strong acids that ionize completely or hydrolyze completely. Weak acids slightly ionize or slightly hydrolyze or hydrolyze. Strong bases have a strong attraction for protons. This would be our Bronsted. Weak base would have a weak attraction. And so here, the strong acid, we would show this as just being one arrow. You know, this is downhill, basically. Whereas a weak acid, you know, is more like this type of scenario where the weak acid just partially ionizes. It's much more favored as molecules. So this would be the major species over here. Over here, this would be the major species over here. And basically, the acid strength is just dictated by how much it ionizes or hydrolyzes. So we have an acid table here. These are all conjugates. So if I have HI, the conjugate base of HI is iodide. And the conjugate base of a strong acid is extremely weak. So if we have a strong acid like HI, its conjugate base is going to be extremely weak. That's a seesaw relationship here. Whereas if we have a weak acid like hydroxide, hydroxide is not even considered an acid usually. It's considered a strong base. But if hydroxide acts as an acid, it loses its proton. In the process of losing its proton, it'll form oxide. Oxide is a very powerful base. So that's a conjugate. And so we have a ranking here, except we have to remember the leveling effect here. You know, the strong, these will have the leveling effect. You can go back and look at the leveling effect, which we talked about before. For the strong. Whereas these ones are ranked, you know, and so increasing strengths. So increasing strength means more hydrolysis, more protons will form. And so the more H plus. And so increasing strength means increasing H plus concentration. I'll put square brackets. The square brackets just refer to concentration. And so these are going to give us the highest concentration of H plus. And the weaker the acid is, the less H plus that's being generated. So let's say one of the stronger weak acids would be something like this. Like oxalic is borderline strong. Whereas when we go down here, when we get to these very weak acids, then we expect very little to make it up, or practically nothing to make it up. And so it depends on how much hydrolysis we have, you know, it's percent hydrolysis. And so up here we expect about 100% hydrolysis. You know, and then down here it's going to be less than 100%. And then way down here it's going to be much, much, much less than 100%. You know, already down here, like I think phosphoric's like 30% hydrolysis, but when we get down here, it's like way less than 1% hydrolysis. You know, less than 1%. Well, you don't have to memorize these, but we can use these rankings to rank the acids and bases and then figure it out. List the following in order of decreasing strength. So this is just look it up on the table. And so we don't have to memorize that. But some things we should be able to do without looking at the table. And so without looking at the table, which would be the stronger acid, like so for example, H2SO4 versus HSO4 minus. Well, this has already lost a proton here, so this is going to be a stronger acid. You know, there's certain things, or base. You know, when we're looking at bases, we could do OH minus versus O2 minus, you know. And so if we take water, water can go either way. So water is going to be the weakest of the bases, and then hydroxide, and then oxide. Oxide's lost all its protons from water, let's say. And so there's certain things that we should be able to figure out without having to look at the figure here. Now, for predicting acid-base reactions, what we do is we just inventory and then we ID the strongest acids and strongest bases present. And so when we predict these, oops, this came out small, sorry. I guess you guys can't really see it, can you? Let me go back to these slides to make sure I didn't blow it up too much. That one, this one. This one. Just basically, we need a driving force. And so what we do is we find the species here that's going to react. And so here we have, let's say, HSO4 minus reacting with hydroxide. And when HSO4 minus reacts, it loses a proton. When it loses a proton, it forms sulfate, its conjugate there. And hydroxide, the base, is going to gain a proton. When it gains a proton, it's going to form water over here. All right, so this is the reactant, this is the reactant, this is the product, this is the product. And so what we do is we compare the two acids. So here we're going downhill. We're going from a stronger acid to weaker acid. And here we're also going downhill. We're going from a stronger base to weaker base. The bases are upside down. And so this is the zigzag pattern. And so we have the zig, zag, zag pattern. And we can figure it out. And so HSO4 minus, what we can say as far as chemical properties go, HSO4 minus reacts with any base stronger than sulfate. SO4 2 minus. And so let's see on this chart here where that puts us. So HSO4 minus here reacts with any base stronger than sulfate. So for example, if it reacts with oxalate, that's favorable. So if HSO4 minus reacts with oxalate, what do we form? Well, we're going to form sulfate. Oh, that's good because oxalate to sulfate is going from a stronger base to a weaker base. And then it's also going to make hydrogen oxalate or bioxalate. Well, that's also good because this is going from a stronger acid to a weaker acid. And so that works out. However, if I tried to get oxalate to react with, not oxalate, let's try to get bisulfate to react with chloride here. Will it react? Okay, so if we have bisulfate reacting with chloride, that means chloride gets the proton to form hydrochloric acid. Well, that's not good because in this case we're going from a weaker acid to a stronger acid. That's not favorable. And then chloride, we have to compare with if bisulfate loses a proton, it's going to form sulfate. Well, that's not good either because going from chloride to sulfate is uphill because we're in the upside down universe over here. And so this is not good either because this is going from a weaker base to a stronger base. And so it's not favorable. So we expect NR or reverse reactions favored. It's not to say it can't happen. Depends on how high the hill is to climb. You know, if this hill climb is too high, you know, then it's difficult. Like here, this hill climb HNO2 to fluoride might not be as high, and so maybe some of the population can react uphill. But that's our zigzag relationship there. And let's continue on here. They're just asking which side is favored. They're just asking which side's the downhill side. And so they're showing all these, and we don't necessarily know if it's even. And so HF versus HSO3 minus. This is the acid, this is the acid, and this is the base, this is the base. And so HF is the acid, HSO3 minus would be its, F minus would be its conjugate base, sorry. And if HSO3 minus is the acid, SO3 2 minus would be its conjugate base. But we don't compare the conjugates, we just look at the acids. So is this uphill or downhill? So we go HF versus HSO3 minus. So HF, which is here, versus HSO3 minus, which is here. And so it's downhill. This is downhill. If that's downhill, then what that means is it's favored. And so this one is favored. Forward direction is downhill. The uphill direction is reverse here. So the products are favored. Forward reaction is favored. They're making comparisons. So, you know, acid-base reactions are proton transfer, whereas redox reactions are electron transfers. One of the big differences here is usually this is just one proton. This is X electrons, you know. So in one sense, the proton transfers are easier because we just look at one proton at a time. In another sense, the electron transfers are more complex because sometimes it's 3 that are gained and 5 that are lost, or some mismatch in number. All right, so this is a Bronsted acid base. We are really not going to look too deeply at Lewis acid base. Now the next thing I want to look at are pH and the water equilibrium. Now, what does it mean? This is pure water, let's say. Pure water has a pH of 7. And so what does that mean? Well, let me tell you what that means. The pH is the power of the hydrogen ion concentration. And the power of the hydrogen ion concentration is given by a logarithmic scale. It's log of the H plus concentration. And so what that means is this. If we were to solve for the H plus concentration, the H plus concentration is equal to 10 to the minus pH molar. And so this is 10 to the minus 7 molar, which is 1. Actually, let me go. 1.0 times 10 to the minus 7 molar is typically what it means. That means to have a pH of 7 means this. pH 7 means we have 1.0. Actually, let me do it to the correct number of sig figs. pH 7.00, this is 2 sig figs. In the power function, this is 2 sig figs. Is 1.0 times 10 to the minus 7 molar H plus. This is 2 sig figs here. And so that means we have acid present in water. But water's pH neutral because water is neutral because the hydroxide ion concentration is also 1.0 times 10 to the minus 7 molar. And so the way neutral is defined in terms of pH is this. Neutral just means that the H plus concentration is equal to the OH minus concentration. Acidic means that the H plus concentration is greater than the OH minus concentration. And basic means that the H plus concentration is less than the OH minus concentration. And so it turns out that all solutions contain both H plus and OH minus. Well, how could that be? And like, for example, all solutions contain both, including pure water. In fact, that's why they contain both. And so why does pure water have, you know, H plus, which is considered Arrhenius acid, and OH minus, which is considered Arrhenius base, both present? And the answer is it's because of the water equilibrium. What we have is we have two waters collide. One water acts as the acid. Actually, let's make the first water the base. And the other acid acts as the acid. And so proton's going to be transferred from the acid to the base. So that's going to form hydronium, and the acid is going to lose that proton, forming hydroxide. And so this is an ionization or self-reaction of water. Now, just a small fraction of water molecules have enough energy to do this. In that small fraction, most of the water molecules don't have enough energy to react. It's actually a tiny fraction because you need quite a high cutoff energy here. And so let's say we had a population of 1 billion, then about 4 out of a billion water molecules will have enough energy to do this. This is extremely uphill. Here. So if I have water plus water, and I have a billion bicyclists here, out of a billion bicyclists, just maybe 4 can make it to the top here to form H3O plus hydroxide. Now, we're going to have a dynamic equilibrium, so there's always going to be about 4 up there. So if these 4 drop down, another 4 will replace, or if 1 drops down, 1 will climb back up. But this reaction is heavily favored to the reverse here. And just a tiny, tiny bit will go forward. And we'll have a dynamic equilibrium set up in water, in pure water. This dynamic equilibrium is going to result in 1.0 times 10 to the minus 7 molar hydronium. Hydronium or H+. This is going to give us pH equal to 7.00. We want 2 sig figs here, 2 sig figs here. And it forms in a 1-to-1 mole ratio with hydroxide. So we're going to have 1.0 times 10 to the minus 7 molar hydroxide. And this gives the power of the hydroxide concentration of 7.00 POH, which we say. All right. This is called the water equilibrium or water KW. Calculate the concentrations of one more species present in each chemical. Well, this is the KW we have here. KW is a constant. This is a constant. For pure water and all solutions. In pure water, the hydrogen ion concentration and the hydroxide are equal. However, in acid solutions, the hydrogen ion concentration goes up. If the hydrogen ion concentration goes up, the hydroxide must go down. In base solutions, the hydroxide solution, hydroxide concentration goes up and the hydrogen ion goes down. So there's a seesaw relationship here. This. And so as the H plus goes up, to maintain this constant, this is a constant, to maintain this constant, the OH minus concentration must go down, and vice versa. If the OH minus concentration goes up in base solution, then that means the H plus concentration has to go down. That's the water equilibrium here. And these are the definitions of neutral, acidic, and basic solution, depending on which one dominates. This is just solving, this for X. If this is just in pure water, this is for pure water. You don't have to worry about this here, up there. So we need some equations here. The equations that we do is KW. KW is equal to H plus times the OH minus, which is equal to 1.0 times 10 to the minus 14. So we could use this, so if we're given one of these, we could solve for the other. So that we're given one. So the H plus is 10 to the minus 5. Therefore, the OH minus must be 10 to the minus 9 so that they add up to 14. And so we could solve that. The other equations that we're going to use is pH is equal to the negative log of the H plus. And these equations are given. You don't have to memorize these. And that the H plus is the anti-log. And so it's 10 to the minus pH molar. Oh, there's one more, and that is the pH plus the pOH is equal to 14.00. They have to add up. And so we look at the power, that is the exponents of these. They have to add up to 14. So let's say the pH is 7. If the pH is 7, then the pOH has got to be 7. Let's say the pH is 9. If pH is 9, then the pOH must be 5, etc. These are examples. Oops, examples. And then we'll say etc. here. So basically with the numbers here, a neutral solution has a pH of 7. Acidic solutions will have a pH less than 7. And basic solutions will have a pH greater than 7. Here we can use these relationships to do the calculations here. The hydroxide and the pOH have the same form as the pH ones here. This is the kW. And this is actually what we call pKW, the power of kW. So if we look at the power of kW, it's actually the negative power. So the negative power is 14. We have 2 sig figs, it's 14.00. So that's the power function here. We're just going to do very simple calculations, so nothing beyond something like this. So I can look at the pOH here. The pOH is the negative log of that, so the pOH is 2. And we don't have any sig figs there. pOH is the negative log. There's an error here. The error here is it's not negative 2, it's positive 2. And that means the pH must be 12. 12 plus 2 will give us 14. It'll add up. And the H plus is 10 to the minus 12 molar. pH is our logarithmic scale, so it goes by powers of 10. So if we have a pH 3 versus a pH of 6, that's 3 orders of magnitude, or 1,000 times stronger. So pH 3 is 1,000 times more acidic than pH. And this would be 10,000 times. This would be 100,000 times. So it's powers of 10. I'm just trying to show it here. That's basically it. This you should know, though. You know, neutral or near neutral, 7. You know, weakly acidic, 4 to 6. Strongly acidic, less than 4. And same thing, just qualitative. We can see certain solutions. So if battery acid, pH 0, stomach acid, pH less than 1, lemon juice is pH 2, very acidic, vinegar is very acidic, pH around 3, wine's around 3.5, tomatoes are quite acidic at 4, black coffee 5, milk is getting close to neutral, pure water 7, blood is just near neutral, just slightly basic, sodium bicarbonate, weak base, borax, weak base, milk magnesia getting stronger, detergents getting stronger, aqueous and ammonia is quite basic, bleach is very basic, sodium hydroxide, very basic. We have pH meters that we can use. This is pH paper, or pH indicator paper. This is a pH meter here we can use to determine pHs. We use these in Chem 1A. All right, for non-integer, we're not going to do a non-integer. We're just going to keep it simple and just do integer values. So, so non-integer, we'll just skip those. You just use the calculator to do it, just to save some time. It's not hard, but we just end up using calculator. You can read through it if you're interested in it. But we'll just do integer. For integer, it's just power. In the exponent, the negative power. And so if the concentration is 10 to the minus 12, then the power will be 12. If the concentration is 10 to the minus 2, the power is 2. That kind of thing. It's orders of magnitude or powers of 10. All right, that concludes this chapter, so I'm going to stop it here, and then we'll do chapter 18. I'll post a video of that probably tomorrow. Okay, bye.